Does
My alarm goes.
I will end.
Okay, then you can take a nap and I take a nap.
Oh, sweet. Wait, oh, wait. This is Tuesday.
No. Usually it's
Okay. All right, ladies and gentlemen. So once again, we have two small units left, one on kinetics and one on equilibrium. Kinetics is very closely related to thermodynamics, like thermochem, in that kinetics is how fast the reaction proceeds. There's going to be a little bit of overlap, like we talked about catalysts last time. So kinetics is the rate of reaction, or how fast the reaction proceeds. Okay, that's what kinetics is. We talked about catalysts before, and remember that catalysts overcome the little energy barrier. So there's reactants and there's products, and they go over the energy barrier. So the catalysts reduce the energy barrier, and then there's this thing called an intermediate. We've always thought about reactions going from all the reactants to all the products. What really happens is most reactions take multiple steps. Let me show what I mean. If you had the reaction A plus B yields C plus D, we've always thought about it as like one linear shot. Boom, from A to B to C to D. But what might be going on is A might be reacting with B to produce I, and then I might be then producing C and D. Okay? The I is called an intermediate. It is something that gets created and then uncreated. I called it the activated complex. We were talking about thermochemistry.
Yeah.
Like you got to get to the activated complex and then it becomes the products. So what might happen is A and B becomes I, and then I becomes C and D. This is called a two-step mechanism. Okay, the mechanism is how something does something. So in reality, very few reactions do what they do in one step. Most of them have multiple steps. It makes an activated complex, and then they eventually make their products. So that's an intermediate, something that gets made in one step and gets used in another step. Give me a thumbs up if that idea makes sense. Okay, it's a little bit new, so I'll make sure we're cool. Again, catalysts are things that are both present as reactants and products. So sometimes you actually see a catalyst present. So let's say this is A plus B plus X becomes C plus D plus X. X is the catalyst. It is present as both a reactant and a product. If something is present as both a reactant and a product, it's a catalyst. It's involved in the mechanism, but doesn't actually get consumed like a reactant, and doesn't really get produced like a product. It is both there as a reactant and a product. Okay. Does that idea make sense? Okay. So a catalyst is something that's there in the mechanism doing its work, but it is neither consumed nor produced, because it's both a reactant and a product. Give me a thumbs up if that idea about catalysts makes sense to you. All right. About half of you, take it. Any questions before we jump right in? Okay. Off we go. Reaction rates. Okay, so when we say reaction rates, what we're talking about is how fast a reaction proceeds. How fast a reactant gets used up, or how fast a product gets made. So when we're talking about reaction rates, we're talking about how fast a reaction proceeds. How fast does it go? And it turns out it's going to be a concentration over time issue we're going to talk about in a second. But it's about how fast reactants get used up and how fast products get made. So what are some things that might speed up or affect how fast a reaction goes?
Temperature.
Temperature. Excellent. Temperature. Because when you increase temperature, what are you really increasing? The kinetic energy, the movement of the particles. So when you're increasing your temperature, you're increasing the kinetic energy of the particles, how fast they're moving, how much oomph they're carrying. So it turns out temperature plays a huge role in how fast reactions go. We're going to investigate that tomorrow in a lab. You're going to do some reactions that are cold, some reactions that are hot, and the hot ones are going to go broop, and the cold ones are going to be like, are we going to be able to finish this in class? It's going so slow. But yeah, temperature plays a huge role. What else plays a role?
Could it be the environment it takes place in? There's like something it's exposed to.
That would be a catalyst presence. Yeah, so there's a catalyst presence. 1 then 2.
Air pressure?
Pressure, yeah. So what does pressure do to gas molecules? Pushes them closer together. So if things are closer together, then they interact more often. Is that what you were going to say?
No.
Okay, what else you got?
Like what type of substances you're using?
Okay. So if you want to meet,
How much of it?
concentration. Concentration is a big one. We're going to investigate that tomorrow too. We're going to do some at half a molar, and some at 1 molar, and some at 1.5 molar, and we're going to measure the reactions as they proceed with more or less stuff. Okay, so if you want to meet people, you want to go where people are. More people, the more people you meet. And the more often you go, the more people you meet. And the more fun you're having, the more people you meet. So reactions are the same thing. Concentration of solutions, if you have a higher concentration, you're going to have a faster reaction. Surface area. Powders react faster than solid chunks. And pressure of gas. Pressure is like concentration for gases. So if you have more stuff in a smaller area, you'll get more interactions, so you'll speed your reaction up. If you have more surface area, when you're talking about solids, you have more surface area, there's more places for the molecules to bang into the stuff, and it'll speed up. And for gases, when they're closer together, because of increased pressure, then they'll speed up. Because what? That doesn't make any sense. Now if I said powders react faster than your mom, because your mom's a big chunk, then that would make sense. And then once again, catalyst presence. If you have a catalyst and you reduce the activation energy required, then that will also speed up the reaction. So remember, all reactions, even very exothermic ones, will have an energy barrier. What a catalyst does is it shrinks the hump, shrinks the energy barrier. You know, your mom's interested in shrinking humps. She's at that hump, you got to shrink the hump. Yeah. It's like, hey, tell me, a catalyst, you shrink that hump. Okay. Some of you are still scribbling. Those of you who are not still scribbling, give me a thumbs up if you understand what we're talking about so far. Question?
No.
Oh.
That was simple.
Okay. So, reaction rates. Question?
So catalysts can only make things go faster, or can they make things go slower?
They can make things go slower too. We can put things in the way, but I don't think they're called catalysts. I could be wrong. If we put things in the way to slow them down, I don't think they're called catalysts. Okay, reaction rates, guys. When we're talking about reaction rates, we're talking about how fast the reactants get used up and how fast the products get made. They always have the unit, write this down, they always have the unit of molarity per second. So, concentration over time. My black pen is biased. Better? So they have the unit concentration divided by time. It's molarity per second. In other words, it's how concentration changes with time. Every second, how much concentration changes. So the rates will always have the concentration, or the unit, molarity per second. Okay, give me a thumbs up if you're ready to move on. Cool. Now that we know what changes reaction rates, we have a way to show what reactants affect reaction rates. And those are called rate laws. So for any reaction, A, B, A plus B makes C and D, the rate is based only on the reactants, and it has this form. Rate equals some constant. The K stands for constant. The concentration of A raised to some power times the concentration of B raised to some power. Okay, that is a rate law. A law, like a formula, like Hess's law or Gibbs law. So a rate multiplied by some constant, and the constant is found experimentally for the reaction, multiplied by the concentration of A raised to some power, multiplied by the concentration of B raised to some power. And this literally is a mathematical exercise. So think about this. If you doubled the concentration of A, so if you doubled the concentration of A and the rate doubled, you doubled the concentration of A and the rate doubled, what is the exponent above the 2? It would be squared, so 2 squared is 2? 1. It would be a 1, because 2 to the first power is 2. So if you double the concentration of A and the rate doubles, we would say it's first order with respect to A. I'm going to show you this in a little bit more detail. So if you doubled A and the rate quadrupled, then it's second power. We would put a 2. We would raise the concentration of A to the second power. What if we doubled A and the concentration went up by 8 times? What's the exponent? 3. We would call this third order. If we change A and the concentration changes by 8 times, it's 2 times Q, a third order. And what if, this is a little weird, watch this. What if we change the concentration of A and there's no change?
0.
0.
Then it's 0 power, right. Anything raised to the 0 is 1. Remember your algebra? Anything raised to the 0 is 1 power. So that's what we're talking about. If you change a reactant, you look at how the rate changed, and you derive the orders of those reactants from the rate. So first order means you doubled A and the rate doubled, or you tripled A and the rate tripled, or you quadrupled A and the rate quadrupled. It did the same thing. It mathematically did, the rate did the same thing as A. By the way, K is not going to change because K is a what? Constant. Do you understand what constant means? Okay. So something that is first order, you double A, it doubles the rate. Second order, you double A, you quadruple the rate. Third order, you double A, you octuple the rate. And 0th order, anything you do to A has no change in the rate. If you want to write that down, go ahead and write that down. I'll give you some time. Surprised they didn't cancel. Good luck. Thank you.
Well, let's just have like 11.
Did the adapter work? Did the video adapter work?
The what?
The laptop adapter, did it work? I thought you were coming to Stuco.
I don't know.
Okay. Okay, well, so somebody, if it's not working, they'll come panic. And I didn't give it to him yesterday. I gave it today. Yeah, so if it doesn't work, they'll come panic me. They're like, fix it during the assembly. I have an adapter that allows the Macintoshes to, the MacBooks to talk to the LCDs. All right, so give me a thumbs up if this idea makes sense to you. Okay, so again, rates are based upon the concentrations of reactants. And some of them play a role. Some of them play a big role. And some of them don't play any role at all. Now here's something that's also very important. Your rate law always has the form rate equals the concentration of the first reactant, concentration of the second reactant. the rate will always have the unit molarity per second. The units of the concentration can change, and will change, which makes it kind of neat. Because if we know the units of the constant, we can kind of cheat a little bit. Let me show you what I mean. Let's say A is first power. If A is first power, then it's just going to be molarity to the first power. And if B is first power, it's going to be molarity to the first power. Right? What do you think the units of the constant have to be?
Oh, seconds.
It has to be, you're going to have a 1 over, you're going to have over seconds. Well, what else do you have? Right now you have molarity seconds.
Okay.
What has to be over here? Or down here? Look at the math. If it's molarity per second on this side, right now it's per second molarity. The constant has to be 1 over ms to cancel out one of the m's. Okay? The rate will always be molarity per second.
It's pretty good.
So the rate constant changes based on the order. So we can kind of cheat a little bit if we know the rate constant. We're like, aha, I know the rate constant, and that means I know it's going to be this many orders. Let me show you what I mean. If the rate has to be molarity per second, and you know the whole reaction is m to m, so if A is second order and B is first order, then you know the constant is 1 over m2s, molarity squared seconds.
So it is. So if is it always the biggest exponent that you have?
No. So let me show you what I mean. If you have molarity per second, and this is, if they're both second order, then this is 1 over molarity cubed seconds. The most important thing is the units have to cancel out, so the rate is always molarity per second. Because this is 4 m's, there's only 1 m here. So 3 of the m's have to cancel out 3 of the m's.
Oh.
So this is, if you write it all out, it's m over s. Canceling them out becomes molarity per second. Your rate will always be molarity per second. So if you know what the rate law is, you can sometimes cheat a little bit to determine the orders of the reactions. Does that idea make sense?
Yes.
So give me a thumbs up if you're ready to move on. Okay, so any questions? I only saw about 5-6 thumbs. Okay, moving on. All right, so how do you get rate laws? Well, you have to do practice. You have to do experiments. And this is what you're going to do tomorrow in lab. So what you do is Rome would do multiple trials of a reaction. He would, in each trial, hold one thing constant and change something else to see how it would change. It's kind of like video games. You change one thing, figure out how the other thing changed, and that allows you to determine how the change happened. So here's a set of data. I don't know why the animation's all blurred up, but here's a sample set of data. Take a look. In experiment 1, in trial 1, we had 1 atmosphere of NO, 1 atmosphere of O2, and the reaction took 30 seconds. Look what happened in experiment 2. What did we change in experiment 2? We changed O2. In O2, we doubled the pressure of O2. And how did the rate change? The time dropped by half, so the reaction went twice as fast, exactly. So if the time took half the time, that means the reaction went twice as fast. Does that make sense? So 30 divided by 15 is 2. We doubled O2. The reaction went twice as fast. What is the order of O2? 1. Exactly. It is 1. Okay. By doubling the O2 and making the reaction go twice as fast, that tells us the oxygen is first order. Does that make sense? Okay. Give me a thumbs up if that makes sense to you.
Is this just
We're
like
getting there.
Is this
Okay.
like a constant, like it'll be the same for any reaction? Or is this just for that one reaction?
Just for this reaction,
Okay.
but the process is always the same. Okay. Look at 1 and 3. What did we change in 1 and 3?
The pressure and
Yeah, we changed the pressure, and how do we change it? We doubled the NO, and look what happened to the rate. What is it?
4.
Yeah, it took 1/4 the time, so it's 4 times the rate. So that tells us that the order of NO is 2. So the rate is some constant that we can find experimentally. NO raised to what power? 2. O2 raised to what power? 1. That is the rate law for that reaction.
That's so cool.
And that's what you're going to be doing this week and early next week. Okay. If this makes sense to you and you understand it, give me a thumbs up. Okay. Question?
So it only matters the first time it changes, because like then O2 goes 1 to 2 again, so that doesn't matter.
The fourth trial, you never need a fourth trial.
Okay.
So you just look at what is held, you hold one constant. In this case, the NO is held constant, and we change O2. In this one, the O2 is held constant, we change NO. In this one, we changed them both. The fourth trial is only there for a check. So if you wanted to go, okay, this one got doubled, and this one got doubled, this would be 2 and 2. That means the rate should go up by 8 times. The fourth trial is there for a check, and it turns out that 30 divided by 3.8 is 8 times. So you can put the numbers in, do your little algebra, and the fourth one's just a check. If you want to use it, great. If you're happy with using just 3 trials, that's great too. All right, with this understanding, I'm going to give you a set of data, and I'd like you to determine what the rate law be. I'm going to write this one down. This one was, you're going to be out of your way in a second. Rate was K, NO raised to the second power, O2 raised to the first power. Okay. So use the data given to you in front of you and determine the rate law for this reaction. Or take a nap. It's entirely up to you. You probably have a test next period. You can take a nap here.
Do we have a test? Rome's just a walking beam. He needs his rest. So that he can be
I don't know why I'm so tired. I'm just
Probably because you stayed up all night playing video games and watching TV.
no,
Hey, season
I actually
4
went to bed pretty early. 9.
Oh, he's just watching.
I went to bed at
What's earlier?
He was watching his Desperate Housewives marathon.
No, he was watching Flexi Labs. To show you the strength of Flexi. This song is boning.
Okay, it sounds like from the chatter either I got you off task or you're finished. Let's take another minute or two.
Mr. Bios.
Yes.
I only have one question. Do you go off of the CO, or like say the CO double? Do you go off of that for how many moles, or do you go off of the reaction?
Still that, you still get
You use both. So you're looking at 2 trials where one thing's held constant, the other thing changes. But another 2 trials where that first thing that was held constant changes, and the second thing that was changed was held constant. We only change one thing at a time.
Yeah, I understand that. But
Okay.
like for the between the first and second, the CO doubled, but the time stayed or the pressure stayed the same.
Right.
So would it be 0? Okay. So you just go off the CO2 after 5 seconds.
Yep. Yeah, this is another way to show rate. If it gives you pressure after a certain amount of time, this is another way to show rate. Oh, by the way, everything in this class is going to be integers or very simple multiples. There's going to be 1.0, 1.5, 2.0, 2.5. You won't have to be like, I got 2.32. What should I make it? Don't worry about that. It's always going to be really simple multiples or integers. You might get a 0.33, but I think that's about the most exotic you'll get. Yeah.
So we don't have to, because I'm a little bit confused.
Okay.
So you don't have to worry about the NO2, really? Is that like...
You absolutely do, because NO2 is a reactant. So you look at a system where the NO2 changes and the CO2 doesn't. That's going to give you the order for the NO2.
Oh.
Okay, so let's just go ahead and work it out. You had a little time to struggle with it. Okay, which reactions did you use, or which experiments did you use to determine CO?